Welcome to Naradar Academy. In this video, we are going to discuss about closure of a set. Okay, first let's start with the definition of adherent point or contact point. A point P in R is said to be an adherent point or otherwise contact point for a set S contained in R if every neighborhood of P contains a point of S. Okay, so what is the condition to be satisfied? Every neighborhood of the point P contains a point of the set S. Okay, this is called what? Adherent point. See, already we have seen what do you mean by limit point. So if a point P is said to be a limit point, then every neighborhood of the point must, that is every neighborhood of the point must contain a point of S other than P. Okay, so if every neighborhood contains a point of S other than P, that point is said to be limit point. But for adherent point, the condition is a little bit relaxed. Okay, so every neighborhood must contain at least a point of S. Okay, it may be P also or different from P also. Okay, right. So this is somehow a relaxed condition from limit point. Okay, so what do we mean by an adherent point? That is, neighborhood intersection with the set is non-empty for every neighborhood n of P. Okay, so the every neighborhood of P must contain a point of S that may be P itself or other than P. Okay, so this point is called adherent point. And the collection of all adherent points of a set S is called closure, and it is denoted by either CL of S or S bar. There in limit points, how do we say? The collection of all limit points is called what? Derived set, and it is denoted by S dash, and here it is closure of S or S bar. Okay, so this is the notation for the collection of all adherent points of a set. Now in this video I am going to discuss few theorems based on closure of a set, and then I am going to discuss problems. That is, if a given set is for a given set, how to find the set of all adherent points. Okay, first let's start with the theorem. The first theorem is, if S is any subset of R, then closure of S is equal to S union S dash. So the closure of any set S is equal to S union S dash. What is this S dash? Derived set. What do you mean by derived set? The collection of all limit points of S. Okay, so closure of S is nothing but the union of the set with its derived set. Okay, this is what we have to prove. So for proving two sets are equal, how do you prove? First you prove left hand side is a subset of the right hand side, and then you prove right hand side is a subset of the left hand side. So in that same way I am going to prove closure of S equal to S union S dash. So let me consider a set S in R. Okay, see, every limit point is also an adherent point. By the definition of limit point and adherent point, what do we conclude? Every limit point is an adherent point. Why it is so? Because limit point means what? Every neighborhood of the point contains a point of S other than P. Okay, that is the limit point. But for adherent point, every neighborhood contains a point of S. So every limit point will become an adherent point. So S dash is always, so derived set, every limit point is an adherent point. No? So S dash is contained in S. Okay. Also, you see every point of the set S is also an adherent point, because the point is within the set only. No. So if you take intersection of any neighborhood of the point with the set, at least you will get the same point. So every point of the set S is also an adherent point. So S is also contained in closure of S. So two conditions we have. S dash is a subset of closure of S, and S is also a subset of closure of S. So together how can we write? S union S dash is a subset of closure of S. So one side of inclusion we have proved here. So S union S dash is a subset of closure of S. The other side of inclusion we have to prove. That is, we have to prove closure of S is contained in S union S dash. So for proving closure of S is contained in S union S dash, I am taking one point P in closure of S. What do you mean by this? P is in closure of S means P is an adherent point for S. That means every neighborhood of P contains a point of S. So here I have two different cases. So every neighborhood of P contains a point of S means the point may be P itself or other than P. Okay. So if the common point is P, then What do you mean by that? N intersection S is equal to P. So P belong to both N and S. In that case, P belong to S. So initially I have taken P is in closure of S. Now I have proved P belongs to S. Okay. What is the other case? That is, since every neighborhood of P contains a point of S and in N intersection S is not equal to P means it is some other point. Okay. So P doesn't belong to S. Okay, right? Now, so from this, what do we conclude? P is an adherent point, but the common point for N and S is not P means every neighborhood of P contains a point of S other than P. Okay, P is not in the intersection means some other point different from P is there in the intersection. That implies what? P is a limit point because every neighborhood of P contains a point of S other than P. So P is a limit point. Limit point means what? It belongs to the derived set S dash. So we have started with P belong to closure of S. Now we have arrived either P belong to S or P belong to S dash. So R means what? Union. So what do we conclude? P belong to S or P belong to S dash implies P belong to S union S dash. Okay. R means union only, no? So P belong to S union S dash. So we have started the point in closure of S and we have proved it belong to S union S dash. That means closure of S is contained in S union S dash. So the other side of inclusion is also proved. So finally what do we conclude? Closure of S equal to S union S dash. So this is an important result. This result only I am going to make use for doing problems. So if a set of real numbers S is given to you, for finding the closure of the set, I am going to make use of this result only. So while doing the problem, I will tell you. Okay. Now let's see the next theorem. The closure of a set S contained in R is the smallest closed superset of S. Okay, so for any subset of R, the set closure is the smallest closed superset. So this theorem I am going to prove in 3 steps. Okay, first step I am going to prove closure of S is the superset of S. So that is the first step. And the next step I am going to prove closure of S is closed. And then I am going to prove closure of S is the smallest superset. Okay, so I am going to prove in the 3 steps. First, let me prove closure of S is the superset of S. So for that, what I have to prove? S is contained in closure of S. This is obvious that we have seen in the previous theorem also. So for proving S contained in closure of S, if you take any point P belongs to S, then whatever neighborhood of P you take, P belong to N intersection S, no? Therefore, N intersection S is non-empty. Therefore, P is an adherent point. So P belong to closure of S. So S is contained in closure of S. That means what? Closure of S is a superset for S. So one part of the theorem is over. What is the second part? I have to prove closure of S is a closed set. So if I want to prove it is closed, I have to prove its complement R minus closure of S is open. So for proving R minus closure of S is open, I have to prove R minus closure of S is neighborhood for each of its points. So for that I am taking one arbitrary point Q belong to R minus closure of S. What do you mean by Q belong to R minus closure of S? That is Q is in the complement of closure of S. No, that means Q doesn't belong to closure of S. So if a point is not in closure of S means what? Every neighborhood of Q does not contain any point of S. Isn't it? So if I randomly take one neighborhood Q minus epsilon to Q plus epsilon, this does not contain any point of S and it is contained in R minus closure of S. Okay, for every epsilon. Okay, for whatever epsilon you take, this is contained in R minus closure of S. Now you combine this step and this step. So we have initially taken one point Q belong to R minus closure of S. Now we have arrived at the point that the interval, the open interval Q minus epsilon to Q plus epsilon is contained in R minus closure of S. This implies Q is an interior point for R minus closure of S. Okay, this Q I have arbitrarily taken. Since this is true for any arbitrary point, what do we conclude? Every point of R minus closure of S is its interior point, isn't it? That means what? R minus closure of S is open. When will you say a set is open? If it is what? If it is neighborhood for each of its points. Otherwise, if every point of the set is its interior point, then the set is said to be open. So here R minus closure of S is open. That means its complement. Closure of S is closed set. So two parts of the theorem is over. That is, we have proved closure of S is superset for S and closure of S is closed. Next I have to prove it is the smallest It is the smallest superset for S. That means if S is contained in some other set T, I have to prove closure of S is contained in T. That means this is the smallest superset. So any other superset you take, okay, then closure of S will be a subset of that set. This is what I have to prove. So now you see, let me take S contained in T. T be a closed superset of S. So what do you mean by T is a closed superset? R minus T is open, and see, T is the superset of S, no? That means what? S is contained within T. Okay? Appo, what we, R minus, that is R minus T intersection S will be empty, no? See, if this is taken to be R, for understanding purpose only, I have drawn it like square and circle. Actually, it is everything is coming in real line only. Okay, if I draw R, S, T in real line, number line, you cannot get the point clearly. That's why for understanding purpose only I draw it as square and circle. Let me take this rectangle as outer rectangle as R, and this is T, and within the T S is lying. So R minus T is open, okay, and R minus T intersection with S is what? Empty. That means any point of R minus T cannot be an adherent point for S. Therefore closure of S is contained in T. So what we have proved, closure of S is the smallest closed superset of S. Okay, next theorem, S set S contained in R is closed if and only if closure of S equal to S. Okay, for any closed set, closure of S is equal to S. So let S be a closed set. Then closure of S is the smallest closed superset, no? So S is equal to closure of S. So one side of the inequality is proved. Sorry, one part of the theorem is over. For the other part, suppose closure of S equal to S, then also S is closed because this is closed, no? So S is also closed. Next theorem, the closure of a set S contained in R is the intersection of all closed supersets of S. Okay, so intersection of all closed supersets. Let T denote the intersection of all C, where C is a closed superset of S. Okay, I want to prove T equal to closure of S. See, T is obviously a superset for S. Okay, and it is also closed. But what we know, closure of S is the smallest closed superset. Therefore, closure of S is contained in T. Next, see, T is the intersection of all closed supersets, no? So, intersection means what? T is also a subset of each of its members. So, T is contained in closure of S. So, by including both the inclusions, what do we conclude? T equal to closure of S. That means closure of S is the intersection of all closed supersets of S. Next, few results for closure. Closure of empty set is equal to empty set. If S is a subset of T, then closure of S is a subset of closure of T. And closure of S union T equal to closure of S union closure of T. And closure of S intersection T is contained in closure of S intersection closure of T. Next, let's see some problems. How to find closure of a given set. See, open interval 0 to infinity. So for finding closure, I am going to make use of the theorem. Closure of S is equal to S union S dash. Okay. So closure of 0 to infinity means, see, just you put closed interval. Okay. So closed interval 0 to infinity. That's all. For infinity, we always used to put open, no? That's why I have put open. Otherwise, for finding closure, just you put what? Closed interval. Similarly, for minus infinity to 0, open at minus infinity, closed at 0. Okay, next one. Set of all 1 plus 1 by 3 power n belong to Z plus. So the closure is equal to, already told you, no, closure is equal to S union S dash. So the set S union with S dash. S dash means what? Derived set. This problem I have already discussed in the limit points video. So there you can see how to find the limit points for this set. This set is having one as the only limit point. So the closure is equal to what? S union S dash. Okay. And similarly for the next problem, R minus 1 by n, where n belong to Z plus. So its closure is equal to R, because for this problem also I found out the limit points. Limit points is equal to R. Okay. So the closure is also equal to R. Next, 1 by m plus 1 by n, where mn belong to Z plus. For this set, the limit points are 0 and 1 by m belong to Z plus. This is S dash for this set. And for closure means what? You have to take S union S dash, no? So this is S union S dash. Okay. The next problem, Q. What about closure of Q? For Q, the limit points, that is Q dash is equal to R, no? So closure of Q is also equal to R. because closure of Q equal to what will become Q union Q dash, no, but Q dash is equal to R, so Q union R equal to R only. Next one is Z. Closure of Z equal to Z union Z dash, but Z dash is empty, no, so closure of Z equal to Z. Similarly for N also, natural numbers, closure of N equal to N union N dash, but N dash derived set is empty, so closure of N equal to N only. And set of all 1 by N belong to Z plus. For this set, 0 is the only limit point, so the closure is equal to 0, singleton 0 union with this set. Okay, that's all. Thank you.